Welcome. In this session, we are going to look at synthesis of purine nucleotides. And when it comes to the synthesis of purine nucleotides, you can either use the de novo pathway or the salvage pathway. In this session, I'll be looking at the de novo pathway. Okay, so the de novo synthesis of purine nucleotides. Okay, that is what I'll be looking at. And welcome all. My name is Wallace Munye, and I'm the unit third. Now, purine nucleotide synthesis. Now, the atoms of the purine ring are contributed by a number of compounds, which include amino acids. Which amino acids? Aspartate, glycine, glutamine. Also, carbon dioxide contributes, but carbon dioxide will come in form of, it will combine with water, then it will be increased to, so it will come in form of a bicarbonate ion. Also, N10 formal tetrahydrofolate will contribute to the formation of the purine ring. Now, this ring is primarily constructed in the liver by a series of reactions that add detonated carbons and nitrogens to a preformed ribose 5-phosphate. Remember, ribose 5-phosphate is synthesized in the pentose phosphate pathway. You can use you can either use the oxidative reactions or the non-oxidative reactions to form ribose 5-phosphate. Let me remind you. Now, let's start here. Glucose, phosphorylated, it is phosphorylated to form glucose 6-phosphate. Then glucose 6-phosphate will undergo these three oxidative, these are the oxidative reactions. 3 oxidative reactions in the pentose phosphate pathway to form ribulose 5-phosphate. Then ribulose 5-phosphate is isomerized by the ribose 5-phosphate isomerase to form ribose 5-phosphate. Okay. Now, when using the non-oxidative reactions, you can take these intermediates of the glycolysis, such as fructose 6-phosphate. You add it to glyceraldehyde 3-phosphate to form erythrose 4-phosphate and xylulose. This xylulose will be converted to ribulose by the phosphopentose epimerase, okay, and it can form ribose 5-phosphate. I hope you can see these reactions. So please, today we are not looking at the pentose phosphate, but we have done a good video on that. Take your time, look at them. Now, this is the purine ring, okay? But let me first, so that I don't confuse some of you. Now, you can see this nitrogen here. It is the first one to be added. This is not the numbering of the elements in the purine ring. This is not how they are numbered. The way I've put them is the way they are usually added. So this is the first one to be added, and it comes from the amino acid glutamine. Then the second, these are the second to be added. This, and this, and they come from glycine. They come from glycine. Okay, let me take my eraser. And this is the third one to be added, and it comes from the N10 formal tetrahydrofolate. Then the fourth atom to be added comes also from glutamine. The fifth atom to be added comes from N10. Sorry, the fifth. The fifth comes from the carbon dioxide. The sixth to be added comes from aspartate, and the last to be added comes from also N10 formal tetrahydrofolate. But when naming them, when numbering now this compound, this is number 1, this is number 1, this is number 2, this is 3, this is 4, this is 5, okay, this is 6. You can see I've gone anti-clockwise, but in the hexagonal ring. But when the 5-membered ring, I will go in a clockwise direction. 6 there, then 7, 8, and the last one 9. And it is this to this ninth, then the nitrogen at position number 9, that is where now the ribose will be attached. Okay, the sugar moiety is attached there. Now let's continue. Now, which is the first reaction? In fact, this is one of the important reaction in purine synthesis, but it is not considered as the first reaction because it is used in other. You will also need this reaction in the salvage pathway, okay, and other reactions. So, but it is important to know it now. 5-phosphoriboside 1-pyrophosphate, PRPP, is an activated pentose that participates in the synthesis and also the salvage of purines and pyrimidines. Okay, that is why, because it is also used in pyrimidines, that is why I have not said it is not like the committed step. It is not the committed step in purine synthesis. Now, synthesis of the phosphoriboside pyrophosphate from ATP and the ribose 5-phosphate is catalyzed by an enzyme known as the phosphoriboside pyrophosphate synthetase, or also known as the ribose phosphate pyrophosphokinase. Okay, and this enzyme is usually X-linked, and it is activated by inorganic phosphate. Okay, but it is inhibited by the purine nucleotide. So there will be a feedback inhibition. Okay. Now, because the sugar moiety of the phospholiposide pyrophosphate is ribose, ribonucleotides are the end products of this de novo purine synthesis, and they are used in the RNA synthesis. Now, when we need deoxyribonucleotides for DNA synthesis, the ribose sugar is the one, it is usually reduced by the ribonucleotide reductase. Okay, and maybe we look at that another time. Now let's start here. You can see this is ribose 5-phosphate. Okay, then we have the phospholiposide pyrophosphate synthetase, also known as the ribose 5-phosphate pyrophosphokinase. To it you add ATP, and what comes out is AMP. Then the pyrophosphate is attached here. Okay, you can see here, it's attached here at the alpha position. This is the alpha position. Okay, here. Now, you can see activated by inorganic phosphate, inhibited by the purine ribonucleotides, the AMP, GMP will contribute to this. Now, the second, now this is the committed step. Okay, this is the committed step in purine nucleotide biosynthesis. Okay, and it is the synthesis of 5-phospholiposide amine from phospholiposide pyrophosphate and glutamine is, as shown in the next slide, is the committed step. Okay, in where the amide group of the glutamine usually replace the pyrophosphate group attached to the carbon number 1 of the phospholiposide pyrophosphate. This is the committed step in purine nucleotide biosynthesis. Now, the enzyme that usually catalyzes this reaction is known as the glutamine phospholiposide pyrophosphate amidotransferase, GPAT. Okay, glutamine, the P represents the phospholiposide pyrophosphate amidotransferase, and is usually inhibited by the purine nucleotides. The IMP will inhibit it, AMP and the GMP. Okay, and the AMP and the GMP act synergistically, in that if both of them are there in high concentration, the inhibition will be more. But if one, say AMP is high, but GMP is low, there will be partial inhibition. Now, the rate of reaction is also controlled by the intracellular concentration of phospholiposide pyrophosphate. The phospholiposide pyrophosphate, in fact, is an activator of GPAT. The glutamine phosphoriboside pyrophosphate amido transferase. Now, this reaction, in fact, now let's get serious and take a pen. Now, you can see this reaction. This is the pyrophosphate here. Okay. Then we take the amine group from glutamine and add it there. But you can see initially here it was attached at the alpha position. But when attaching the amine group, you don't attach it to the alpha position, you attach it at the beta position. Okay, please note that. And this is characterized by GPAT. Okay, and this is the committed step for purine nucleotide biosynthesis. Okay, please note that. Activated by PRPP, inhibited by the end products AMP, GMP. Please note that. Now, after forming 5-phosphoribosyl amine, what is the next reaction? Next reaction, we take glycine, okay, and an ATP. Remember, if the enzymes which usually catalyze a reaction where ATP is invested, they are always known as synthetases. Synthetases, okay, a synthetase. Now, what will happen here? You can see we take a portion of glycine, this portion, this one, and add it to the amide group. The amine group here, okay, it's attached there. Okay, and this reaction is catalyzed by the glycinamide ribonucleotide synthetase. Okay, please note that. And this, the compound form will be now the glycinamide ribonucleotide, also known as the ribotide, but let's call it ribonucleotide. Okay, this is the glycinamide ribonucleotide. Then the next reaction, after attaching this, which is the next reaction? Now, or the reaction, I can call it the third reaction. The third reaction, because this was the committed reaction, the committed step. So it can be step number 1 here, step number 2, step number 3 here. Now, in step number 3, we bring in a formyl group. How does a formyl group look like? Let me draw you a formyl group, a carbon there, a hydrogen there. Then to this carbon, you have a double bond to oxygen there. That is a formyl group, and it is attached to tetrahydrofolate. Okay. Then this group is attached to here, this amine group there. To form this, you can see it is attached to there. Yeah, it's attached there. By now, this enzyme that catalyzes this reaction is known as the glycinamide ribonucleotide formyl transferase, also known as the transformylase. Formyl transferase or the formyl transferase or transformylase is the same enzyme. Okay, to form this now is known as the, you can see we have a formyl group attached to a nitrogen. So N-formyl glycinamide ribonucleotide, FGA. Okay, you have just attached a formyl to glycinamide ribonucleotide, N-formyl glycinamide ribonucleotide. Then the next reaction, we bring in glutamine. Okay, glutamine, you also put in some ATP, so it must be a synthetase, the name of the enzyme, and some water. In fact, this water usually hydrolyzes the glutamine to produce glutamate and an ammonia, an amine group. Okay, the amine group is the one which will be added, and in fact, it usually is added at this position. This I'm trying to point here. We remove that oxygen, and we put in this group here. Okay, okay, can see, and the ATP is hydrolyzed to ADP and PI. So then now let's try to name this new compound. It is also an N-formyl, because this is a formyl group, N-formyl. Now it is not a glycinamide, now it is a glycinamidine. glycinamidine, okay, ribonucleotide. F-gam, N-formyl glycinamidine ribonucleotide, F-gam, okay. Please note that, and it is characterized by the F-gam synthetase, okay. This is a glycinamide, but this is a glycinamidine, okay. After that, the next reaction, we will carry out cyclization. We cyclize, we form a bond here, yeah, okay. And this reaction is characterized by an enzyme known as 5-aminoimidazole ribonucleotide synthetase, okay. Because you can see you are putting in ATP, which is hydrolyzed, okay. In fact, I think some water is lost, if I'm not wrong, okay. And you can see this ring here we are forming. This is the first one, position number 1, 2, 3, 4, 5. Sorry, this is now 5 here. Carbon number 5 there. To carbon number 5, you have an amino group. So it is 5 amino. The ring itself is an imidazole ring. So 5 amino imidazole ribonucleotide air. Okay. Then here I will not follow this route. Okay. After forming this air, in fact, we have another route here. Let me draw it, where we first form N carboxyamine imidazole ribonucleotide. What happens in this reaction? We take in a CO2, in form of a bicarbonate ion. We add it to this. You see this nitrogen here? We add it there. So the carboxy group is added to the nitrogen. That is why N-carboxyaminoimidazole. Then this undergoes it is converted now to this, the carboxyaminoimidazole ribonucleotide by an enzyme known as, sorry, here did not say the enzyme. You are putting in a CO2 in form of a bicarbonate ion. This reaction is catalyzed by an enzyme known as N-care, or the N-carboxyaminoimidazole ribonucleotide synthetase, okay? Synthetase. Then this we transfer, now we transfer that carboxyl group from the N position, from the N position at carbon number 5 to carbon number 4. We attach it there, as shown here. Attach it there. So initially it was here, then it moved here. So moving, so it is a mutase. So it is known as the N-carboxyaminoimidazole ribonucleotide mutase. Okay, we form now the carboxyaminoimidazole ribonucleotide. Okay, so this reaction here, I tend to somehow disagree with it. Now, after forming the carboxyaminoimidazole ribonucleotide, next we take the amino acid aspartate, and you can see we are using an ATP, which is hydrolyzed to ADP and PI to form. You can see now this aspartate is added to, because this carbon here has double bond, one double bond to oxygen, one oxygen, and a single bond to another oxygen here, but it will have a negative charge. To this one with the negative charge, that is where the aspartate is added. You can see it is added there, and here it is. Okay, the aspartate is added there to form this compound, which has the very long name, very not wrong, jina mrefu 5-aminoimidazole 4 into bracket N-succinyl carboxyamide ribonucleotide, psychia. Okay. You can also find some text coding it there. The N-succinyl 5-aminoimidazole carboxyamide ribonucleotide. That is where psychia comes from. N-succinyl 5-aminoimidazole carboxyamide ribonucleotide. See the taste. That is the name of the enzyme that catalyzes that reaction. Now, in the next reaction, we remove the carbon skeleton of the aspartate to cut it from at this position. Cut it from there, and one of the hydrogen from here will be transferred to here. Okay, will be transferred there by an enzyme known as the psychia. Here I also psychia, not psychia, psycha. This is the N-succinyl 5-aminoimidazole carboxyamide ribonucleotide. Okay, lyase. Okay, so we click at that position, and the carbon skeleton of aspartate is fumarate, and it will go to the maybe TCA cycle. To form this, you can see one of the, if you removed one hydrogen here, you form a double bond between these carbons, as shown here, double bond. But here you remain with NH2. Okay. Now, the new compound form after the cleavage is known as the 5-aminoimidazole 4-carboxyamide ribonucleotide, ICA. Okay. Then the last reaction where we are adding another element to the Purine ring before we cyclize is catalyzed by the ICA transformylase or the formyl transferase, where the formyl group will come from N10 formyl tetrahydrofolate. Okay, to form this new compound known as the, and see the formyl group is added to this nitrogen at position number 5. So it is 5-formamidazole 4-carboxamide ribonucleotide, 5 here. Okay. Then after forming 5 here, we just need to close the gap here. Just close the gap. So we cyclize and then dehydrate. So by an enzyme known as the inosine monophosphate cyclohydrolase, remove water. Okay, we remove water to form our inosine 5 monophosphate. Okay, so if you look at this Purine, which Purine ring is this? This is the hypoxanthine. This is hypoxanthine. Okay, but when it is in form of a nucleotide, it is inosine monophosphate. Okay, see it. You can see it there. Now we have some reactions which we can inhibit. Now, in this reaction can be inhibited. These two reactions where we are formulating is like adding formyl group, or we are carrying out formulation. You can either use para-aminobenzoic acid analogs. Remember, in the synthesis of folate in bacteria, because humans, as humans cannot synthesize folate, but bacteria can. They usually take the para-aminobenzoic acid and the pteridine. Okay, they combine them to form a product known as a dihydropteridine, which will be then catalyzed to form a folic acid. No need to struggle with that. But if you have a para-aminobenzoic acid analogs, you can prevent the formation of the folic acid. So such analogs are sulfonamides. Okay. And these sulfonamides will only inhibit folic synthesis in the bacteria. So it will prevent, and remember here you are forming nucleotides, which are important in DNA formation and RNA. So those bacteria cannot replicate. But humans, these sulfonamides cannot affect human cells because human cells do not synthesize folic acid. Also, you can use folic acid analogs such as methoxylates. Okay, this drug which is used in the chemotherapy, but this will affect now the human cells. Especially it affects the rapidly dividing cells, such as the erythropoietic cells, the skin cells. That is why people who are undergoing chemotherapy, they might be anemic. It will also affect the cells of the GIT. That is why they have GIT disturbances, those guys who undergo chemotherapy. Because it affects the skin cells, it will cause those guys to have scaly skin. Also, it affects those cells that lead to hair formation. That is why there is hair loss. Okay, because the folic acid analogs, they are affecting folic acid synthesis in the body, not folic acid. Conversion of now folic acid, usually convert folic acid to now tetrahydrofolate. So this drug, methotrexate. Now the methotrexate usually inhibit an enzyme known as the dihydrofolate reductase. Okay, and the hydrofolate reductase is important in conversion of folic acid into tetrahydrofolate. Okay, I think now up to here we have formed inosine monophosphate, but inosine monophosphate you don't find it in DNA. You don't find it in the messenger RNA, but you can find it in transfer RNA. Transfer RNA, you can find it. Now, how do we form now AMP and GMP from inosine? That is what we are going to look at. Here, we already have your inosine monophosphate here. Now, we take another aspartate. For the case of adenosine, if we want to synthesize adenosine monophosphate, you take an aspartate, okay, and a GTP. Please note here we are using GTP. And this, if you are forming AMP, which will finally form ATP, I don't see the sense of you using ATP to drive this reaction. So you use GTP, reaction catalyzed by adenylosuccinate synthetase. Remember some texts usually say that adenylosuccinate synthetase and Cica synthetase are the same, but myself, let's say this is adenylosuccinate synthetase, and the one for the synthesis of Cica is Cica synthetase. Okay, so after that you add aspartate at this position here. Let's see, aspartate is added there. Then you remove the carbon skeleton of aspartate in form of fumarate, a reaction catalyzed by adenylosuccinate lyase to form adenosine monophosphate. Now, this adenosine monophosphate can be converted back to inosine monophosphate by the adenosine monophosphate deaminase. Okay, please remember the purine nucleotide cycle. Purine nucleotide cycle. Okay, in fact, it is just this reaction you are missing, the one from AMP to IMP by the AMP deaminase, and you will convert glutamate to glutamine. Please remember that. Okay, now we have performed the AMP. Now AMP, when in high concentration, it will inhibit adenylosuccinate synthetase. Okay, please understand that. And when after if it is this reaction is inhibited, we will proceed in this direction. What if now you want to form GMP? IMP will be dehydrogenated by the IMP dehydrogenase. You add water and NAD, get NADH and the hydrogen. So you go to the electron transport chain to form um, XMP. Okay, this is XMP. This is santhine. Okay, this building ring here is santhine. Okay, XMP. Now XMP, you to XMP now here, we remove this oxygen and add an amine group there. So you put in glutamine to get glutamate, reaction catalyzed by the guanosine monophosphate synthetase. Okay, see utilization of ATP now to form guanosine monophosphate. Now this is guanosine. Now, guanosine also, when in high concentration, will inhibit inosine monophosphate dehydrogenase. Okay, now, but inosine monophosphate dehydrogenase itself is usually inhibited by this drug, this acid known as, it is a drug actually, mycophenolic acid. Okay, and this one mainly inhibits it in rapidly dividing lymphocytes. Okay, rapidly dividing lymphocytes, and it is usually used in the as an immunosuppressant. Okay, immunosuppressant when one has like after carrying out organ transplant to prevent rejection, you can use this immunosuppressant. Okay, I think that was the end, and it has been good. I hope you have understood, and please subscribe for more anatomy and biochemistry content. Thank you.